Hello, everybody. Nick Gubbins from Colorado State University, back again, this time to talk to you about weathering in the environment. So, the learning objectives for this video, by the end of it, students will be able to understand the difference between physical and chemical weathering, see that the world around us is constantly weathering, and understand where weathering is more or less intense, and then the factors that underlie that. So I know I hinted at it, we hit on it a little bit in the solubility lecture, but what is weathering? Weathering is just the process through which minerals are broken down. So here is an arch in Jordan that has been eroded by wind, and erosion is just one type of weathering. So there's two main types of weathering. We have physical and chemical weathering. And so physical weathering, like what I just brought up, erosion, is the mechanical breakdown from physical force of minerals. So that can be a force from wind, from water, from ice, through cooling and heating, through tectonic action, through biology, anything. So a couple examples of this. So the arch from my first slide and here, that has been eroded by wind. So that's a good example of erosion. The boulder in the top left, that has been cracked from freezing and thawing over intense winters and summers. We can see rocks being cracked by tree roots in the bottom left, forcing their way through, and then a channel that's being eroded by water through rock. So erosion is a big one to think of, but then also things like mass wasting, so landslides, can play a part. The other type of weathering is chemical weathering. And for this, water is very, very important. Because essentially, most of chemical weathering is how are minerals being dissolved. And so those solubility effects all come into play there. So there's a bunch of different chemical reactions that we call chemical weathering. So some of the more common ones is hydrolysis. So that's when water reacts with surrounding minerals and loosens its bonds. Carbonation, oxidation and reduction, dissolution, here's carbonation, as I was saying, and then there's also biologically mediated ones. So to step through some pictures here, hydrolysis, so water loosening the bonds in minerals, is a big step in clay formation, which is the image on the right there. Feldspar has been hydrolyzed into clay. The top left is a good example of dissolution or carbonation. So that's limestone, which is mostly calcite, which you've seen a bunch of times in this course. But that is weathered into being dissolved into water. And then the bottom left with all those dramatic colors, that is a good example of biological weathering, but that's the oxidation of iron by bacteria in pools by a volcano. So the key concept here is that there's two different kinds of weathering. Physical weathering is the mechanical breakdown of minerals, and chemical weathering is the reaction and dissolution of minerals. All right, before we go too much further, let's do a quick review of the second law of thermodynamics, because it's been a minute. So that second law says that the entropy of the universe is ever increasing. So if you remember, entropy is the state of disorder. And it says that all spontaneous processes must increase entropy. And in an isolated system, this means that concentrated energy is going to disperse over time. So if you have some ordered compound, like in the top left, over time that is going to break apart. And so with that in mind, when we ask ourselves when do things weather, the Shawshank Redemption quote, you either get busy living or get busy dying, comes to mind. Either something is pumping energy into you all the time and you are fighting entropy, or you are weathering. So everything in contact with something else, everything with potential energy in it, be that physical or chemical, all the time, is weathering. So let's talk about that with a few examples. So if we look at the thermodynamics of a mountain, at some point a bunch of energy was spent into pushing that mountain up. And so at the very top of the mountain, we have really high gravitational potential energy. So those rocks up there have a bunch of potential energy in them. And down at the bottom is a state of lower gravitational potential energy. And so over time, entropy will increase, and the things up at the top, what goes up, will come down. And that potential energy will be dispersed into kinetic energy of moving particles and slowing down water and sediments being dragged down the mountain. So another example, a chemical example here instead of physical, is the thermodynamics of carbonate weathering. So calcite, this CaCO3 that you've seen a million times by now, it looks something like this. This is obviously an abstraction, but that's the mineral structure of it. It has a lattice to it, and that lattice eventually will dissolve in water to create bicarbonate, and it will look something like this. And so in the crystal structure, there is a lot of potential energy to keep it locked in that low entropy state. And then in its dissolved form, that mineral structure is gone, and that potential energy has been dissolved off into kinetic energy in the water. And so entropy increases as it dissolves. And so this is a good example of a hydrolysis reaction here as well, but of it lowering the order of the products into the reactants. All right, so the key concept here is everything is weathering constantly. So we know that everything's weathering, but not everything's weathering at the same rate. So what controls that rate? How fast do things weather? So that is controlled by a couple of things, namely the parent material, so what is being weathered, the climate around what's being weathered, the soils over it, and its exposure to all the above. So let's launch right into these factors. So the parent material is one of the primary controls of weathering, and it sets the baseline because the mineral composition, in our solubility lecture, we discussed that certain things are more soluble than others, and more soluble things are more easily weathered, especially chemically, and structures that are mineral structures that are more robust and are more tightly packed are also then more stable and more resilient to mechanical weathering. And so if you remember to your kinetics, the reaction rates for any given reaction is partially determined by the accessible surface area in that reaction, and that is something that parent material also can determine. So on our continuum here of really fast weathering to really slow weathering, starting on the left here on the top, that is a big old pile of glacial till. So that's ground that a glacier has already mechanically weathered. And you can see that all the rocks in it have been broken up, and there's a bunch of loose sediment and whatnot. And so that has a lot of surface area and will weather very quickly. And many of its constituent parts, so if there's limestone in there, for example, which is the example just below it, that's a very soft rock. It's mostly made out of calcite. And that is something that will weather very quickly. And if it was insulated by some other rock in that pile, that would stop it from being weathered before. But now that it's all in one big jumble, it can be weathered quickly. In the middle there is a granite boulder. And so that's made out of a much more recalcitrant mineral. But it's been split by that thermal weathering, thermomechanical weathering that I had mentioned before. And then way off on the end of the slowest right here would be some large mountain that has very little surface area compared to its volume. So here's a figure from a very great textbook, Biogeochemistry Analysis of Global Change. And this is a sequence. Up at the top here are the most weatherable minerals. And so we have things like olivine or feldspar. And then at each stage in these arrows here, a weathering reaction can occur to essentially remove some of its structure and leave some solid left. And we'll get more into this in future lectures. But the important thing to note here is that these top forms here are very weatherable. And then by the time you get all the way down to quartz, you have a very tight crystal structure. and it is very resilient to weathering. Another way to look at this would be the relative stability of common minerals under weathering, and so these have a bunch of different minerals here off on the left, and then this shows the rates at which they weather. And so you can see things like calcite is one of the fastest weathering things, and then something like feldspar is in the middle, and then something like quartz is up near the top of this list. So next control here is climate, and this is a big one. And so the general rule here is that hot and wet is going to be faster than cold and dry. And this is really important. Water is a huge deal in weathering sequences, not only because of things like hydrolysis and carbonation, where water is itself doing the weathering, but also because, if you remember back to your kinetics lectures, water will move away the weathered products, which essentially makes refreshes the gradient and allows more things to dissolve in. So if water is constantly flowing over a landscape, it greatly increases how quickly things can weather, both from the chemical reaction and from the gradient perspective. And so places like rainforest, tropical rainforest, we would expect to be super, super fast weathering. So from left to right here, we have this is in the Kilimanjaro rainforest, and you can see there's rivers running over everything. It's constantly wet, it's constantly hot, and you'd have really fast weathering rates. So moving right is then Hoosier National Forest in Indiana, a temperate forest with temperate climate, and so that has some heat, has hot summers, cold winters. That would be faster than, say, Antarctica, which is cold but has some water seasonally flowing over it, and that would be even faster than the Gobi Desert, which is both very cold and very dry generally. Temperature is very important. Again, from your kinetics, if you remember, temperature is the master control on how fast reactions proceed, and so hotter places will generally have faster weathering rates. So really cool figure here from a 2014 paper. These Hartman et al., they went ahead and created a global model for chemical weathering rates, that's CWR, for the entire world. And they have a couple of different figures in their paper that describe the effect of soils, the effect of other things. But this is their base model that's just based on the water data that they have and the temperature and climate values that they have. And you can see, so blue here is very fast weathering rates, and then red is very slow weathering rates. And so in places like the southwestern US, so in the deserts of the US, very slow weathering rates. In places like the Amazon rainforest, very high weathering rates. Australia, very low. Oceania, very high. And that ultimately comes down to climate. Climate. Let's see. The next control is soils. And soils play a really important role because they both retain water, they host vegetation, but then they also basically create small little micro environments next to the things being weathered. And that can have really important effects on pH, on gradients, on all sorts of things. So again, from left to right for sort of the prototypical examples, rainforest soils are very hydrated, so there's a ton of water in them, and they usually have extensive root networks that are constantly busting them up. They're full of life and bacteria. And then something like a clay series here in the middle. And then off to the right would be some very well-drained soil, like a sand dune, which doesn't have much life in it, and water that's in it quickly drains out of it. Another control is exposure. And so this is sort of a catch-all for a lot of the other effects, because exposure is rolled into, parent material or climate and water and all of that. But it's basically how long is the material exposed to all of these other things. And so you can imagine in like a soil profile, like the soil that is at the very top with plant roots in it and water falling onto it is going to weather very, very fast. And then in the middle, something like the middle of this soil profile here, we'd expect slower weathering rates because it's being insulated by that layer of topsoil. And then the slowest rates would be something like bedrock that has meters and meters of soil and saprolites and all sorts of things above it, insulating it from water, from heat, from light, from everything. So a final point on weathering rates is that we as humans mess them up in a big way. So we like to add reactable surface area by blowing up mountainsides, which is pictured here, or doing construction or plowing fields, and all of this increases reactable surface area and brings new, usually lower exposure minerals to the surface. And we also change the chemistry of our environment. We burn a lot of fossil fuels, and we lower the pH of water and of the environment generally. And we also divert water all over the place. And so we can put water over areas that had not weathered previously, therefore creating new weathering, essentially. And then also, we change the climate. And like I had hit on earlier in this lecture, climate is a huge, huge driver of weathering rates. And so as the climate becomes hotter and wetter, we would expect for weathering rates to pick up as well. So the key concept here is weathering rates vary by location, and they're limited by their parent material, the climate, the soils, and their exposure lengths. All right, bonus material. So climate controls weathering, but weathering also controls climate. So here we have a schematic of silicate weathering, and it has a negative feedback loop with a hotter and hotter runaway climate. So as silicate minerals are weathered, they can convert CO2 into bicarbonate ions that can later become precipitated out in the ocean, therefore burying that CO2. Okay, bonus material. So climate controls weathering, but weathering also controls climate. So here we have a schematic from a cool paper that was looking at paleo weathering, but it describes the feedback loop between weathering and climate. So we know that hotter and wetter climates should increase weathering rates. And so they will weather more things like silicates, which here you can see is idealized as wollastonite, so CaSiO3. And so as that is weathered, it's going to add silicates and calcium into the water, but it's going to be weathered by acidified water, so CO2 basically dissolving into rainwater to be slightly acidic. And then that bicarbonate ion, once it makes it to the ocean, can be precipitated out with calcium as calcium carbonate and can become buried. So effectively, as more and more CO2 is put into the atmosphere, we'd expect the temperature of the globe to rise and increase weathering rates, and then with higher temperatures and more precipitation, we have more weathering, and then with more weathering, we'll be burying more CO2, and then that will in turn reduce the changing climate. And so this operates over like geologic time scale, but this is one of the master controls over geologic time on Earth's climate system. Another little slice of bonus material here is soils control weathering, but weathering also controls soil. So I hit on this a bit with the exposure, but you can see here that soils up at the top of this profile, here's a dramatic one where they cut through to make a new road. Soils at the top are really, really highly weathered, and then they're insulating the next layer underneath them. So it's being weathered by water, but at much lower temperatures and with much less water running through it. And then that is acting as an insulator to the unaltered rock underneath it. And so how soils form, the acidity that they hold, the water that they hold is also, it's going to play a part in weathering rates and how the underlying parent material gets weathered in the future. Cool. Well, thank you so much for sitting down with me to learn about weathering, and I'll be back to talk about weathering concepts.